We try to give them time to run over there. The cello all the way over, right?
Well, I have my cello music with me, so I don't.
Smart.
I have a locker, so, because that would be really.
That would be really hard all the way there. It's hard to get there in 10 minutes anyway, let alone with the cello. Okay, I think we're ready to go now. Definition, a sequence an is Cauchy if and only if for each epsilon there's a positive integer n, such that if m and n are greater than or equal to capital N, then an minus am is less than epsilon. What is the difference between this and convergent?
Greater than?
Yeah.
Or equal to?
That's instead of the.
That should be a limit right there.
Yeah.
If it was convergent, then that would be the limit. So for the limit, you'd have for all n greater than capital N, you'd have an minus a is less than epsilon, rather than an minus an. Well, we're not assuming a limit yet. We're going to get to showing there as well. But yeah. Yeah, that's one of the values in your sequence. So what is the same? Can we draw a picture of it then? Suppose you have your sequence, and I'm going to make one that's going to kind of jump around. So it says you get to choose an epsilon neighborhood so that after some finite amount of time, all your points are inside that epsilon neighborhood. That distance from each other is less than epsilon. Well, it's actually 2 epsilon, epsilon up and epsilon down. That's what Cauchy means. The terms in your sequence get close together. Not that your terms get close to the limit, but that the terms in the tail of your sequence get arbitrarily close together. They almost get non-differentiable from each other. You can almost hardly tell that they're not the same terms. Okay? That's what Cauchy is saying. In the tails of the sequence, the terms get very, very close together. So, looking at these right here, which of these sequences that just flashed by, did you get them all, are Cauchy? Let's try this again. So let's check and see. What's the first term when n equals 1? 1/2? What's the second one? Yeah, 2/3. So it looks like this is going to have a limit of 1, but does that make it Cauchy? So what's making it Cauchy? What's the difference between 1/2 and 2/3? Yeah, 1 is smaller, but what is it? If you did 2/3 minus 1/2, what do you get?
Good answer.
That is, it's a Microsoft answer. Completely accurate and absolutely useless. 4/6 minus 3/6, you get 1/6. Now, tell me what would be the difference if you subtracted those two, 1/2 and 4/5. I'm going to do 4/5 minus 1/2. Would be 8 minus 5/10. Now compare 3/10 and 1/6. They're smaller than 1/2, right? They're both smaller than 1/2, right? And if I keep going out, the answer, the difference between them is going to be less than 1/2. So now let's start with 3/4 and subtract those two, 3/4 and 4/5. So 4/5 minus 3/4. 16 minus 15/20. So that's 1/20. So that's getting smaller. And this right here, in fact, that's going to be less than 1/4. Why am I choosing 1/4? That's how far 3/4 is from 1. So the difference from 3/4 in any of the terms after that is going to be something less than 1/4. right? And if you go farther out, what is the difference from 5/6 and all the rest of the terms? 1/6. They're all going to be less than 1/6. How about if you were at 9/10? What would be that difference? Less than 1/10. Is it Cauchy? Yeah, the terms are getting closer and closer together. So this is Cauchy. Now,
Will they get closer and closer?
yeah, the terms themselves have to get closer and closer together. So you have to subtract terms and see if they're getting smaller and smaller. Mm-hmm.
Yeah, they are.
Then it's not Cauchy.
Like you have to try it out a lot of times or something.
Yeah, we're actually going to have ways of determining
I
Cauchy.
figured.
Yeah.
Like,
This is sort of the brute force method.
the number two is not.
Always have to do the long way first. Huh?
Always the long way first.
Always the rest of it seems
That's like you got this, like, derivatives using the.
Well, that way you learn the definition. Oh, by the way, we're going to be doing that in analysis.
Oh, this analysis or
This analysis. So this one is not Cauchy. Next analysis, we're going to be doing integrals the long way using the summations. So yeah,
I don't need
It's
it
fun.
out, too. I just need one.
Aw.
Analysis too.
Oh, yeah, I'm not in there.
Well, how many of you have math education? Well, there's going to be 2 of you then. Oh wait, Clyde, did you raise your hand? Are you math education? So there's 3 of you in analysis too. It'll be fun. I've actually taught analysis with just 1 student before.
It's good smaller. On the
I
right
feel like
side,
I'm
any
gonna-
question you had, you get direct contact with the teacher.
True. Yes.
Have
I
the
feel like
top
that'd be
grade
so
class.
weird.
Yeah.
You'll be the top of the lab.
And if you're failing everything, the curve is always in your favor.
This is true. It would be in your favor.
It's about like Dr. Anderson curve.
And at that point, I just lecture on paper and then I hand you the stack of paper when we're done because why post it online if you're the only person looking it up?
Maybe you want to share it with your friends.
There is that. Okay, anyway, Dustin answered number 2. Why is he correct on that?
The terms don't get closer in intervals.
Yeah.
They don't. Yeah, the intervals stay the same. So if you look at this, you have 1, 2, 3, 4, 5. They don't get closer and closer together. Do what, Cauchy? Yeah. Yeah. There you go. So this one would be 1, 4, 9.
Way further.
Yeah, they're getting farther and farther apart. So this one is also not Cauchy.
So which means n to the power of fraction maybe.
Depends on what the fraction is. Because if it's a square root or cube root or something like that, then the answer is false.
Like,
But if it's the nth root of n,
yeah,
n to the 1 over n, this actually converges, oddly enough. I think. I have to think about that. I know if it's a constant to 1 over n, it converges to 1. Oh, remember when we did in Calc 2 and I said, okay, you have to do the limit taking y equals and do the natural log of both sides? Yeah, that's that whole process. We're not going to do that right now. So if you have a constant raised to the 1 over n, then that would end up being Cauchy because it converges to 1. Tell me about this next one. The first one is going to be 101. Yeah, then it's 100 plus what? 1/4, 100, 1/9, 100, 1/16. Keeps on going. So this one is Cauchy because those fractional amounts are getting smaller and smaller, so it's approaching 100. In fact, what we're going to find out is if it's convergent, then it is Cauchy.
Oh, that's true.
Okay, now because you have to do this on your homework, we should do one in class so we know how to do this. Prove that the sequence is Cauchy. Here again, we have to fix our epsilon. This is just like our limit definition. Fix epsilon greater than 0. Let n be in the naturals. You guys like J. Such that n is going to be bigger, and we have to fill in the blank here. Then for all n and m greater than or equal to capital N, we have, now let's plug it in. We're going to have 2n plus 1 over n minus 2m plus 1 over m. Yeah, that comes from the definition. Now, we have to do algebra. Arithmetic. Adding or subtracting fractions. That means we have to get, yes. So 2nm plus m minus 2nm plus n. And put that second one in parentheses so you don't lose the minus sign. And you have over n times m. Does anything cancel?
2 in it.
Yeah, those are going to cancel. You have m minus n over n m. Now, we would really like to be able to make this in terms of our capital N. Well, we don't have any. What do we do with m and n's? We have two variables going on. We'd really like to get it down to one variable. So I would apply the triangle inequality. This would be m over nm plus n over nm. This is by a triangle inequality. When you do triangle inequality, you turn the minus n into a plus sign in the numerator. Let me not skip steps. I'll put that step in there so you guys can see it. So I'm going to split this up and write it as m over nm minus n over nm, right? And now I can take the apply the triangle inequality, and that becomes, yeah. But all of these are positive, so I can write it as m over nm plus n over nm. Now, in that first fraction, does anything cancel? Mm-hmm. The m's cancel and you get 1 over n. How about in that second fraction? N's cancel and you get 1 over m. Now, way back up here at the top, oh, that was too far at the top. What did we say n and m were bigger than? Capital N. So then I know that 1 over n is less than 1 over capital N, and 1 over m is less than 1 over capital N. See how we turned it into just our capital N's? That was our goal. Turn it all into capital N's. Yeah. Now let's go do our scratch work. We have 2 over n less than epsilon. What is n going to be bigger than? Yeah, 2 over epsilon. So this is going to be less than 2 over epsilon, which is equal to what?
Epsilon.
So as soon as I get the absolute value less than epsilon, I know it is Cauchy. Very, very similar. The only difference is that you're only plugging in the term twice.
That's why that 2 theorems is the same.
Yeah.
It keeps making me write 3s.
Oh, when I forget who was in my office. I was writing upside down for someone, and I was trying to write epsilons, and I was writing 3s instead. Yeah, it just wasn't working. I can't get them right side up.
Let's try to get your attention, Dr.
I'm actually
Anderson.
better at writing epsilon than I am.
What is it? That looks like a 3.
Yeah, that should be a 3, yeah.
Is 3 written to the left? No.
3,
Okay, yeah, sorry.
That looks weird now.
epsilon.
You know what's funny is I'm actually better at writing epsilon. Like even growing up, some I always write 3
Backwards.
backwards. For a while. And so now, like this is like.
Backwards 3, and we like it.
Yes.
It was.
And you know what? If you would look at it this way, it becomes 3 in my language.
Oh, really?
Rotate
That
it.
is.
Like that epsilon, just rotate it.
So like an M
Like an
then.
M.
Oh my. That had to be hard to get used to English then.
Yeah, it's 3.
It's a 3.
Wow, that's annoying. So what's the
Yeah.
No, that is just alphabet.
Okay, back to Cauchy sequences. Here's the theorem I promised you'd be able to use to tell if a sequence was Cauchy. Every convergent sequence is a Cauchy sequence. Yeah, it is short. So what is it telling you? What would be the contrapositive of this theorem? That would be the converse.
Oh.
Contrapositive is negate. Yeah.
Every
No,
not
it's
Cauchy sequence,
Divergent.
not convergent,
Yeah.
not every
Exactly.
Cauchy sequence, there exists non-convergent.
Okay, so maybe we should write this. If it is convergent, then it is Cauchy.
If a Cauchy sequence is not,
If it is not
Convergent.
if sequence is not Cauchy, then it's not convergent.
not Cauchy,
There.
then not convergent. Yeah, but we have to write it in P implies Q. Yeah. You guys should be seeing that, those of you who are tutoring. Set there in logic, in survey of math, they should be asking you those questions.
Is that there in logic?
In survey, yeah. Yeah.
You know
We
what?
don't do proofs.
Uh,
We do truth tables and intersections and unions and complements of sets. No proofs.
I remember
No.
grading that was the first time I saw most of that.
Yeah.
My freshman year, I graded survey of math, and I saw that. I was like, what does this stuff even mean? Okay, well, I have a book here. It's math, you know?
I can tell if it's right or not. Yep.
Yep.
So the contrapositive, remember the contrapositive and the original statement have the same truth values? So every convergent sequence is a Cauchy sequence. If it is not a convergent sequence, then it is not Cauchy. So there gives ways for you to tell if something is not a Cauchy sequence. If your sequence does not converge, then it cannot be Cauchy. Now, this is all with a proviso that we're talking about Euclidean space. In other words, we have to be using our distance formula in Euclidean space for our absolute value formula for distance. Because if you start getting into infinite dimensional things, you can have Cauchy sequences which do not converge.
Oh. Yikes.
Well, then.
That's a
But-
number. Terrible.
That's a long time from now. We're not ever going to get into that here. We keep everything finite for you guys. Go to graduate school and you'll do infinite dimensions.
Doctoral work?
Master's degree.
Oh.
But yeah, that's just a proviso here.
Basically, everything will be-
No, we're just doing, there's actually different spaces in
Geometry,
mathematics.
you'll understand.
Yeah, there's different geometries, there's different spaces in mathematics. We are only studying Euclidean space, 2 dimensions for what we're doing, X and Y.
So you take those in grad school, so what do you take in PhD?
There's no difference between a master's and a PhD except doing your dissertation. You take what they call reading classes, which are classes specialized in your area that's usually 1 professor and 2 or 3 students, and they'll do a specialty class, 2 or 3 of those, and then you do your research for your dissertation. So all the regular coursework is the same as a master's degree. If you're going to get a master's degree, you might as well go on and get your PhD. There's really not that much difference other than you have to write a dissertation.
How long
Like
it take?
200 pages, right?
Oh, mine was less than 100.
Less than 100? Wow, still a lot.
By the time you get around to writing it, though, it's not hard. It was a lot easier to write than some of those 20-page papers that you have to write for English classes.
Yeah. That's
I'm not even gonna do it.
Yeah. So by the time you get around to writing it, it's not that difficult to write. You are prepared to write it. It's not hard. You just have to be tenacious enough to have gotten to that point and not quit because you were so tired of math by the time you get there.
Writing about it.
You eat, sleep, and, whatever. It's just math in your life at that point. Okay, so let's see if we can prove this. Every convergent sequence is a Cauchy sequence. What's the hypothesis?
What was that sequence?
Yeah, so let's call it AN. Let A and B convergent, or let it converge. Okay, so we'll go with your because then I can give what it's going to converge to. So let AN converge to capital A. We're trying to show Cauchy. The definition of Cauchy has a epsilon in it, so we need to fix our epsilon. Yep, so fix epsilon greater than 0. Since AN converges to A, I know there exists a capital N in the naturals such that for all n greater than or equal to capital N, we have, what's our definition of convergent?
Yeah.
I'm going to submit to you that we're actually going to want this to be an epsilon over 2, and I'll show you why. What?
No, I was saying,
Yeah, that's in the book about it. Now, watch carefully. This is so cute. And so for all n and m greater than or equal to capital N, we're just going to apply the triangle inequality. Remember, our goal is to show AN minus AM is going to be less than epsilon. That's our goal. By the triangle inequality, well, first of all, I'm going to add and subtract capital A. You remember that from reading it? And then apply the triangle inequality. But each of these, by the hypothesis right here, is less than epsilon over 2. What is epsilon over 2 plus epsilon over 2? Epsilon. Thus, AN is Cauchy. That's exactly why I wanted epsilon over 2. Because when I add it together, I get epsilon.
wait, is that making a long string?
Yeah. Question.
It says that AN minus A is less than epsilon over 2, but why is A minus A less than epsilon?
Okay, so I skipped too many steps.
I'm sorry. No, I just found
That's all right. That's why we're going to add the steps.
By the way,
Or, I think, I know.
the definition set is only less than.
When you
epsilon.
switch, yeah, in absolute value, you can switch the terms. So you have AN minus AM minus A. And then this was for M bigger than capital N. And up here, this was for all N. So it should work for this M also, because they're both bigger than that same capital N. So that's where we get epsilon over 2. And then that's equal to epsilon. Yeah,
But
Claire.
but how you can set it to be equal to epsilon over 2?
Yeah, why?
When the definition set is just less than epsilon.
When you're applying convergence, you can choose whatever value you want for that epsilon, because you know it works for all of them.
Oh, yeah, because
So,
epsilon is.
yeah. So you're taking the epsilon that someone is using for Cauchy, and you're going to replace the original epsilon for convergent with epsilon over 2. It's just a number.
Does that mean we can put that absolute value is less than 3 any epsilon over any?
any number as long as it's a finite positive number. Yeah. You can choose that. That constant won't change it. Okay, any other questions on that? So let's look at the next theorem. Every Cauchy sequence is bounded. So what's the hypothesis for this one?
Suppose that it's then
Yeah, be Cauchy. Now, what did it mean to be bounded?
above and below.
Bounded from above and below. In other words, you have an is less than m for some m in the positive reals. Okay. So what we're going to do is we're going to assume an is Cauchy. Here, since I'm applying Cauchy, I'm going to choose epsilon to be equal to something. What value would we like? It just has to be a positive number.
1.
Okay, we'll choose epsilon equal to 1. That's what the book used. Fix epsilon equal to 1. Then I know there exists an n in the naturals such that for all n and m greater than capital N, and this is just the definition of Cauchy, an minus am is less than 1. In particular, what I can rewrite is an minus a capital N is less than 1. I'm replacing this a sub m with a capital N because that is, it just says that m has to be greater than or equal to capital N. So I have a particular term here, and these terms are going to range throughout. So by definition of absolute value, we're going to have minus 1 is less than an minus a capital N is less than 1. Add your a capital N to both sides. Now, what I'm going to note is minus the absolute value of a capital N minus 1 is less than a capital N minus 1. It's less than a sub n. It's less than a capital N plus 1, which is less than the absolute value. So this is a negative of that side right there. And now I can combine it together. That's a lowercase n. And absolute value has to be less than a capital N plus 1. Well, that means this is for all n greater than capital N. So I've got all of these n's are bounded. I just have to find a bound for the first finite number of them up to that capital N. So we're going to let m be equal to the maximum of the set absolute value A1, absolute value of A2, absolute value of AN, absolute value of A sub n plus 1. Now, do you guys believe me when I say that everything in this sequence is bounded by n? Thus, my sequence A sub n is bounded. That should remind you of the bounded proof we did for convergent sequences. Yeah. It's identical to that one, except we had to start with A sub m minus A sub n. So those are very similar proofs. Okay, Where we're headed now is the Bolzano-Weierstrass theorem. Bolzano-Weierstrass theorem is the big theorem in this section, and it's one of 3 major theorems in analysis that we're going to see. Bolzano-Weierstrass. Let S be a set of real numbers. This is accumulation point. We're getting ready for it. Yeah. No, we're not there yet. Bolzano-Weierstrass theorem's coming. We have to get accumulation points. Let S be a set of real numbers. A real number A is an accumulation point of S if and only if every neighborhood of A contains infinitely many points of S different from A. Now, the definition in your book left this different from A out. It supposed that it was there, but they explained it later, but they left it out of the definition. If you go in general and look on a general analysis book, they're going to put that phrase in there. It's not going to be assumed.
Why did we not?
They should have included it. They should have been precise enough to include it. Yeah, write it in your book. So you have infinitely many points of S that are different from A. So naturally, we are going to look at accumulation points. Find the accumulation point for this set right here. Different from A. That was the definition. It's on the near the bottom of page 39.
Yeah.
Yeah,
Here. And then here at the bottom, here's where they say it.
Yeah. It was in the paragraph, but they didn't put it actually in the definition.
I don't know, because I saw that it said it.
Yeah. Yeah, it's supposed to say it there. So what is an accumulation point for that first sequence? One over n is a sequence. We have to find something that has infinitely many terms in every neighborhood around it. So if I find a point, we'll call it right here, and I look in this neighborhood, I need an infinite number of those terms in that neighborhood right there. Maybe they're above it, maybe they're below it, but they have to be in that neighborhood. And then when I make that neighborhood smaller, I still have to have an infinite number of terms in it. I would submit to you, it probably should be a limit. You guys remember reading that? Accumulation points are limits of sequences that are not identically constant. So what would the accumulation point be for this first one? 0. The next one has 2 accumulation points. Oh, sorry, has no accumulation points. Why? It's a little bit different than that. It's because it repeats. You have 0 repeating a whole bunch of times, and you have 1 repeating a whole bunch of times. But you don't have any values different from 0 and 1. So if you had told me 1.1 was accumulation point, then I would choose epsilon to be 1 over 100. And now you don't have any points different from 1 in that interval around 1 over 100 of 1.1. They have to be different. They can't be the same. Yeah,
Can you explain why you choose 0 and
limit of the sequence.
so since they are just positive numbers, so you have to have how to make it.
Yeah, I was confused because if you take 2 ranges around 0, you have no values in this.
It doesn't have to be negative. So if you look at 0, if you said, here's 0, and maybe this was minus 1/10 and this is 1/10. When n is bigger than 10, 1 over n is in this interval because you have 1 over 11, 1 over 12, 1 over 13. They're all there. They are not negative. That's okay. But the neighborhood still contains an infinite number of terms. Different from 0. But these over here don't have neighborhoods around 0 or around 1 that contain an infinite number of terms different from 0 or different from 1. So no accumulation point there. Tell me about the next one. 2, negative 2, 1. Well, let's actually graph these and see what they look like. Well, I'll graph them on the horizontal line. That'll be easier. So here's -2, here's 2. So you have 2, -2, then you're going to have 1, and I got this out of order, but okay, and then 3/2, and then -3/2, and then 1 1/4. 3/2 is right here. 1 1/4 is right here. Minus 1 1/4. This was supposed to be 3/2. I got them out of order. I'm not doing well today. Minus 1 1/4 comes down here. 1 1/3 is going to be here. Minus 1 1/3 is going to be here. So all the negative ones are going to where? -1. So negative goes to -1. Where does the positives go to? 1. So look at these right here. 1. Is there an infinite number of terms in any neighborhood around 1? Yeah. Are those terms different from 1? Yeah. So this one has 2 accumulation points. They are 1 and -1. Both of them have an infinite number of terms different from 1 and -1 in every neighborhood. So they have to be the limit of some subsequence of your original sequence. Tell me about the set 1, 2, 3, 4. No accumulation point. It's a finite set. You can't have an infinite number of terms coming from a finite set.
Does that mean they have to put in accumulation point? That's why I asked about accumulation point.
Yeah, you have to have an infinite number of terms that approach the point. So your accumulation point is a limit point that has a sequence converging to it that is distinct from it. It's different from that point. Tell me about this one. 1, 2, 3, 4, and keeps on going. Well, there's an infinite number of terms. Is there no limit? So no accumulation point. So what this tells you is it needs to be a bounded sequence of infinite terms. That if you're going to have a hope of accumulation point, you need a bounded sequence of infinite number of distinct terms. Okay, so where are we headed with this? Let S be a set of real numbers, then A is an accumulation point of S if and only if each neighborhood of A contains a member of S different from A. That is rewording of the definition. We're actually not going to prove that one. Okay, if you have an infinite number of terms different from A, then you have at least one term different from A. And you're good. Finite sets can have no accumulation point. And for an infinite sequence of distinct terms, the limit of the sequence is accumulation point for the set making up the sequence, as long as they are distinct terms. They have to be distinct terms. Okay. Every real number is an accumulation point of the set of rational numbers. Every real number is an accumulation point of the set of irrational numbers. How would we prove this one? I'm actually not going to prove it, but how would you prove it? What did they use to prove this in the book? Well, maybe we'll prove one of them. We'll prove the rational one. So we're going to let R be in the real numbers. And now we have to construct a sequence approaching R, right? So for each, I'm going to choose an n in the naturals instead of an epsilon. You can use an epsilon, it doesn't matter, but I'm going to be able to make my sequence notation with this better. So for each n in the naturals, there exists, we're looking at rational numbers, a Q in the rationals between R and R plus 1 over n. That is by one of our theorems that we proved a couple times ago, by a theorem in chapter 0. Between any two real numbers is a rational number. Call this, I'm going to call it a Q sub n. Then Q sub n is a sequence converging to R. And I'm choosing it between R and R plus 1 over n. I should actually be a little bit more careful, and I should choose the first one between R and R plus 1, and then the next one between R and Q1, and then the next one, so let me do that. I need to be particular so that they're distinct. Let me write this up prettier. So there exists, I'm going to call it a Q1 in the rationals between R and R plus 1. And there exists a Q, that's a G, a Q2 in the rationals between R and Q1. And there exists a Q3 in the rationals between what two values? Continuing in this fashion. For each n in the natural numbers, there exists a Q sub n in the rationals between R and R sub and Q sub n minus 1. So where are these numbers going? Where are these QNs going then? Q1 was 1, what was a number between R and R plus 1. Q2 is a number between R and R plus Q1. So I'm forcing, if you think about this is R plus 1. Here's your Q1, and then in between here you're going to have some Q2, and closer than that you're going to have some Q3. So where are these numbers going? Yeah. Q1 is converging to R. Thus, R is an accumulation point. Of the rationals. And you do a similar proof for the other one. I'm wanting to get to Bolzano's Weierstrass theorem, so. But
They do that in that one, don't
they do what?
they? In that theorem that you're about to.
Yeah, it's the exact same thing, similar as we do this with the rationals.
Oh, I proved the wrong one.
Yeah, they did.
But it's going to be identical.
Wow.
Yeah. I should have looked at that one.
It's all right.
Yeah.
That's done like the first half of the proof.
Yeah. Oh, they did use epsilon. So you have to be careful, though, that you're not picking the same value right at R. Okay. So I gave you a little bit different proof than what they did. Okay. Note that an accumulation point exists under two conditions. The set must be infinite. The finite set didn't work. And the set must be bounded. We noted both of those. And the reason we note that is Bolzano-Weierstrass theorem. forevermore in this class, we're going to call it BW, Bolzano-Weierstrass. So you don't have to remember how to spell that thing. Yeah, there's enough steps on the outline of this one. This one's a long one. But it's actually not, I mean, the idea of it isn't that hard, because the idea of it is that if you have a bounded infinite set, maybe it goes from here to here, you have a lower bound and you have an upper bound for your set, and your set is in here someplace. So you're going to cut the set in half. Either half lives there or half, infinite number lives in the right half or the left half, or both. Pick one of those. Cut that one in half. And you construct this nested sequence of sets that are going to have a limit supremum.
Yeah, it makes sense.
So the whole proof of it's not hard. It's just writing it out as a pain, which we are now going to do.
Lovely.
So what should we start with? We need a bounded infinite set. The book called it S. So we're going to start with S. Yeah. Okay. Since it's bounded, by definition of bounded, they called it alpha and beta. There exists alpha and beta in the reals such that alpha is less than or equal to S is less than or equal to beta for all S in our capital set S. Okay, and they wrote it this way. And so I know that S is a subset of the interval alpha to beta. Okay. Find the midpoint of this interval. They call the midpoint alpha 1. No, that's supposed to be an alpha comma beta.
Oh.
Yeah. So let alpha 1 be the midpoint of alpha and beta. Might have been shorter to just write the formula, but that's okay. And so either alpha to alpha 1 or alpha 1 to beta contains an infinite number of terms of S. It could be both. If it's both, we're just going to pick one. We're just going to say, call A1 and B1. Yeah, though they're using these as closed sets. You can do open sets, it doesn't matter. Call A1, B1, this, no, I gotta reword it. Call this set containing an infinite number of terms, A1, B1. So if it was the first one, then I know that A1 would be alpha 1 and B1 would be beta. No, if it was the first one, it would be A1 is equal to alpha and B1 is equal to alpha 1. If it's the second one, then A1 is equal to alpha 1 and B1 is equal to beta. Okay, now we're going to repeat this process. First of all, I want to show you that the length of A1 to B1 is going to be 1/2 the length of alpha to beta. Okay. Repeat this process. To get another set, and it's going to be A2 to B2. It's a subset of A1, B1, and containing an infinite number of terms of S. And then tell me about the length. B1 minus A1 is 1/2. Oh, so B2 minus A2, sorry, is 1/2 B1 minus A1, but that's 1/2 squared, right? Beta minus alpha. If we continue in this fashion, we're going to make a nested sequence of sets. And they're going to be AN to BN, subset AN minus 1, BN minus 1, subset of A1, B1, subset of alpha to beta, such that AN to BN contains an infinite number of terms of S. And tell me about the length.
And of Bn minus and equal to 2.
Yeah, beta minus alpha. Okay, now what did they do? Remember the whole goal of this is to show it has an accumulation point. The accumulation point they're going to pick to be the limit supremum. And what did they call it? T. Yeah. So first of all, they define their set Q. These are not the rational numbers. Q is all the ANs, such that N is in the rational numbers. And we're going to let T be the supremum of Q. Okay. And we're going to show that T is going to be a bound. Okay? So we need to, well, an accumulation point. We need to show that every neighborhood of T contains infinitely many points. So what we're going to do is fix epsilon greater than 0 to get a neighborhood of T. Then T minus epsilon is less than T, right? If T is the upper bound, the greatest lower bound, least upper bound, I'm going to get them backwards now. Least upper bound is the supremum, so it's the smallest of the upper bounds. Is T minus epsilon an upper bound? It's smaller than all the upper bounds, right? Yeah. Then T minus epsilon is not an upper bound. And hence, I know there exists an A sub n in Q such that T minus epsilon is less than A sub n is less than T. This tells me that I have an infinite number, I have a AN here in each of these epsilons that's going to be between T minus epsilon and T. So you make epsilon smaller, I'm going to get a new AN, and it's going to march in. So that tells you, which theorem do they use? Oh, they're actually going to prove it. Let's go ahead and prove it. You don't have a theorem. I thought we had this, what they claim next is in a theorem. No. So this is our T minus epsilon less than AN is less than T. Then what did they do? What about all the terms, all the M terms? Yeah. For all M greater than this than this lowercase n, I know that AM has to be greater than or equal to AN because the sequence is going in. And so the left-hand bounds have to be going in. So these AMs are bigger. And hence we're going to have T minus epsilon is less than AN is less than or equal to AM. But that has to be smaller than our supremum, our T. Yeah, that's T is the highest part. So they all have to be less than or equal to T. So what we want to do is conclude then that we have an infinite number of terms in our neighborhood. Neighborhood T minus epsilon to T plus epsilon. I didn't even talk about that half. I only went up to T. This contains all the terms A sub m for m greater than or equal to n, and hence contains an infinite number of terms of AM. Now, if all of those A sub n were part of S, we'd be done. But we don't know that. If we did, we'd be good. But what do we know if we could find a bound small enough so that inside T minus epsilon to T, if that set could contain our A sub n and B sub n? So if we found something small enough so that the two values would be less than that, but that's where everything comes from our formula for the A sub n, B sub n minus A sub n. We know that formula. We know that distance on that. So that's what we're going to do. Oh, I'm going to need more space. End page. This one is a long proof. Yeah.
This is
No,
part
it-
of my baby. Graduate school, but
No, this is about where you get in graduate school. Yeah, they really don't get, yeah. You'll see some that are longer than this, but very few that are longer than this. Yeah. This is about, yeah, give or take a little. But you'll see one or two that are longer than this, but this is one of the longer ones. No, those are usually, my dissertation has many, many, many proofs in it. And in fact, my dissertation can be broken up into about 4 different parts that are kind of separate topics that overlap a little bit. So yeah, they're not all over the same thing. Anyway, so let's finish this. So what we're going to do is we're going to choose M in the naturals. I've been calling the naturals J because this book does. We're going to choose M in the naturals, M greater than or equal to N, such that, yeah, just go. You can watch the rest of it later. We're recording it for you. We're almost done. Such that 2 to the minus M, then you're going to have your beta minus alpha is going to be less than epsilon. So that then would force it, this should be a T plus epsilon. That would then force it to be in that interval. Okay, so if this is going to be less than epsilon, this interval has a length of 2 epsilon. And so if someplace, here's our T minus epsilon, Here's t plus epsilon. Someplace over here is our t, and we're going to have an a sub n. So if we have this is less than epsilon, then that means starting from here, it can't go too far. So it forces it to be in the set. So choose this so it's less than epsilon. Then what do we know? I'm going to make this a capital M. So it doesn't look like my, I think I had M's above. I don't want it to be that M there. Then what do I know? Then the interval A sub capital M to B sub capital M is going to be entirely contained in T minus epsilon to T plus epsilon. Do you guys all see that? Okay. How many terms does that interval contain from S? Infinite number of terms. And these are capital M's. So what do I know? Yeah. And so T is an accumulation point for S. Yeah. Accumulation point. So what does that tell you? That was what we were trying to prove. Every bounded infinite set of real numbers has at least one accumulation point. I'm just going to say conclude. And then,
That's it. So that's all that proof is?
yes, very powerful.
It's a baby proof.
Maybe proof.
I'll actually start here next time. There's one other theorem we needed to look at, but homework is still due. Yeah. What was your question, Lubeth? It's on the homework. Yeah, the homework for this section is still due. You can still do the homework for this section without every Cauchy sequence is convergent. That one's
So,
an easy one.
For today homework, we are not extended by history.
No,
Now you want to extend it before you do?
no.
You extended the other assignment, who's like, oh, no, don't extend it, we don't need an extension.
If it were just math majors in that class, I wouldn't have extended it, but I have some computer science people who don't know how to do those proofs.
You have some math people who have issues with
That could be the case too, but
And who have a geometry test tomorrow. And who have geometry test tomorrow and a calculus assignment due tomorrow that's taking forever. And
Let's talk about it.
what work to go to tonight
Yep.
and
sleep,
somewhere in there.
sleep. Yes, that's important.
Notice, well, sleep in class.
I actually didn't notice you were falling asleep. I saw you doze off there for a little while. Then I saw you get up. I figured that was to try and
Class,
wake
you don't
yourself
fall
up.
asleep in class. Like, I've never fallen asleep in class.
I had a religion professor as an undergraduate. I really liked him. He was an incredible teacher, but he had such a wonderful voice that he would put me to sleep. But it was really fascinating because it was Daniel and Revelation, which is my favorite topic. So I really enjoyed the topic, but
I couldn't stay awake to save myself.
I see you guys, I'll see
I
you
don't
later.
know, I feel
guys.
like falling asleep is
Oops,
like the worst thing ever. So, wait, for this one, okay, rest of them.
Finish this one.
This one? I assume one paper
No.
is improved with the other one.
Yeah.
Let's
See,
talk about
yeah, I
geometry.
thought the Higgs word is so good. We have, there exists an M. Show up. Yeah, it does. Let me write it up for you. I can't do it. Small n.
okay. So you know that AM converges to A, and so you're going to fix your epsilon greater than 0.
Right.
Then there exists a capital N, such that for all n greater than capital N, you have an minus a is less than epsilon. And then here's where you're gonna get to the next one. It's so easy, it's hard. So then for all n greater than capital N, you're gonna have epsilon is greater than an minus a minus 0, which tells you that an minus a converges to 0. So you still have to fix your epsilon, you have to get your capital N, write down the definition of convergence, and then apply it to the second. Then you go back the other direction just the same way. That makes sense? Yeah. And you said you got the other ones then?
The last one, I'm not fully sure. This one, the convergence to dynamic sympathy. Oh, so if it's epsilon, then again, you know how I can.
Okay, so here, it exists an alpha and such that for all n greater than capital A is equal to A. That is your hypothesis, and you need all of that beyond that. So if I went here, okay, and then you're not gonna let n be anything, you're actually literally gonna say, then for all n greater than, so you're just gonna go straight to that. Because you already have an n defined, so you're just gonna use that. For all n greater than capital N, we have n minus alpha is actually gonna be equal to alpha minus alpha. So n minus zero, so it's an epsilon, but the convergence mark is good. So yeah, you got that one basically right.
Okay, and then these ones, I'm really fuzzy on my log and explain all of that. And I'm not quite sure how to relate.
So if you were picking the first one, you can have x equals to log plus b, and y equals to log. Actually, you can put that there, it's useful.
How?
So we're just going to do log plus b. So then you're going to have n x equals to b, and e to the y. Then, so you can do either this one, this, if you want to get to the ends of it, that one have an x on it. Or if you want to use the b's, you can make that one have a y. It doesn't matter. I'm going to actually just do that side by x. So e to the y is x equal to x. So that means e to the y so then we just put it back in that next one.
Okay.
Make sense? And then the last one, you're gonna do the same thing, x equals to y plus b, and y is equal to log is one over b. We have x equals to b, and one over y is equal to one over b. So you have one over x over y is equal to b, one over y is equal to b, and we can do the
Okay, so I'm just using the,
This
this
is
to this is equal to this, that kind of, okay.
That's all you
I
do.
think that.
Okay.
Nice detail.
Yes, I know. Okay.
I can write it down.
It is the middle of September. Okay, I'll let you raise card then. I'm gonna put this in my office and post it.